Hello everyone. Today I'm teaching to an empty classroom, so I think I will just record everything that I would like to say about the examples on GurobiPy, and then those of you who have difficulties understanding programming down the optimization with GurobiPy can rewatch it later. So let's begin by looking at the example. So I'm here on the Gurobi optimization resource webpage. It has several nice examples about integer or linear or quadratic programming problems. There's a variety of those examples from the level of beginning to the advanced level. You can take a look at them yourself. I will go over 2 or 3 examples right now and discuss how to construct models for them. So first of all, our favorite example or the favorite system is the electric power system. We have a problem that is called the unit commitment problem. It goes as follows. You have several types of generators. In this particular case, you have 3 types of generators. Each type, you have a certain number of each type of generators. 12 for the type 0, 10 for the type 1, and 2 for the type and 5 for the type 2. You can think about them as different, like a gas generator, a coal generator, and a nuclear generator. For each of the generators, you have a minimum output and the maximum output, and you have a like operational cost for each of the generator. If you are using a generator for an hour, even on the minimal setting, you have to pay a fixed amount per hour, and then on every megawatt over the minimal amount, you have to pay a certain number of dollars per megawatt. In order to turn on a generator, you have to pay a startup cost, but you can turn it off for free. So each generator can operate into different settings, being on or being off. You have a 24 time horizon, and you have predicted demand for each of the time periods. So 12 p.m. to 6 a.m. and then 6 a.m. to 9 a.m. and so on. The demand is in megawatts. You are required to construct an integer programming problem that expresses the optimal schedule to turn generators on and off, and assign necessary production per generator. You also have a constraint on safety, which means that if the demand is predicted inaccurately, you still have an option of going slightly above, and therefore, at each point of time, you must have to have the ability to increase the output of the generators, so that the total output is 150% of the predicted demand. So let's take a look at what are the parameters and decision variables in this problem. First of all, the sets and indices. You have the types of generators, T. You have periods of time from 0 to 4th, so five periods of time. You have parameters in the problem. First of all, the number of hours in each time period. Then the number of generators of type T. you have the total power demand for period P. We assume that it's distributed evenly over the time period. Then we have a number of generators that are on at the beginning of our operation, so that you don't have to pay startup costs for them. You have minimum output of a generator. You have maximum amount of generator. You have the base cost, which is the minimum operating cost per hour of a generator. You have the cost per megawatt that is above the cost to generate 1 megawatt per hour above the minimum of the generator, and you have the startup cost for a generator. The decision variables are going to be the number of generators of type T that are on period P, the output of from the generators of type T in period P. So we are not going to be assigning output to specific generators. We're going to be assigning output to the generators of a specific type. And also we need a variable to express the number of generators of type T to start in period P. Okay, so let's take a look at the objective function. We aim to minimize the cost of operation that consists of 3 terms. First of all, it's the term that corresponds to those generators that are on, plus the extra. Okay, so let's take a look at this. So basically, the first term is the one that corresponds to the base costs of operating a generator. Then we have the cost of operating generators on a higher output level than the minimal one. So we have the current output of a type of generators minus the minimal load, and then we have the startup cost that is available for that we need to count for all of the generators that are being started in time period P. Okay, so now we need to take a look at the constraints. The available generators are limited. So the total number of working generators is going to be limited above by the total number of available generators. The demand is going to be satisfied by the sum of all of the outputs of all of the types of the generators, and minimum and maximum amount of generation essentially you need to make sure that your output is in fact in between the minimal amount of available power and the maximum amount of available power, given that you are operating with this number of generators. Okay, and now the safety constraint that requires us to be able to generate with currently available generators. We have to be able to generate at least 115% of the total predicted demand at period P. So this is 150% of the total demand at period P, and this is the maximum amount of power that we can possibly generate with the generators that are turned on. And now we need to make sure that the startup variable is in fact is possessing its desired property that it should possess by definition. Sorry. This can be achieved by making sure that the total number of generators that is turned on of a specific type is less than or equal than the total number of generators that are being turned on, being operational in the previous type step, plus the number of generators that we could possibly turn on. Okay, now the Python implementation of this model goes as follows. We need to input the parameters of the model and define the model and the variables with add_vars method. Each of the variables gets its own domain, for example, the integer domain or the continuous domain for the output of generators. And after that, we need to take care of the constraints. So we one by one encode the constraints. This one belongs to the generator count, the number of generators that are available in total. So this is the first available generators constraint. The next is the total power output of a generator. So this is implementing this couple of constraints. Then the constraint that makes sure that we are meeting the demand and providing the sufficient reserve capacity. And then the startup constraint that is written it's actually written in two separate constraints, because we have certain number of generators that are being operated and in the zero time period. So we have some legacy from the previous time periods when we did not operate. We were not operating the system. Now we would need to define the objective. We are using the clicksum a method every time we are defining a summation. So this is an important and a very important method in GurobiPy, I would say, because it allows us to define both objectives and constraints in a very simple manner. So we would need to define the active, the z on is represented with active, then z extra is represented with the variable per megawatt, and then z startup is this variable startup objective. And now our eventual objective is just the sum of the three. You can also specify that you would like to minimize, but it's assumed by default, so you don't need to specify anything in this particular case. And now you can write down the model and optimize it. Let's actually try to run this entire thing. So make a copy of this notebook. Okay, so we are installing GurobiPy in this notebook, and then executing all of the cells one by one. Okay, so we have got the solution quite easily. We can check that our objective we have solved to global optimality. Tells us that the gap is 0%, so we did solve it to global optimality. That's great. Now we can take a look at what exactly are the unit commitments. How many units and to which power generation can we commit here? So for that we use pandas data frame. Our rows are the type of the generator, and then we're gonna be representing how many how many generators of each type is being used in each time period. So essentially for each type of the generator, for each period, we need to know how many generators are on at each step. So we can see that step 0 is being operated all the time at the maximal number, the maximal capacity, right? Because we had 12 of them in total, and the type 1 is being turned off in the first time period. Then we use the type 1 is being almost off in the first time period. Then we are using some number of them, but we never use really all of them because we have 10 of them. And type 2 are really being switched on only in the third time period, which corresponds to the peak of the demand, because it's most probably it's the evening when all the people are turning on their appliances. The following shows the number of generators of each type that must be started in each time period. So how many generators are we starting? We are starting pretty much like a lot of them of type 0 in the very first time period, and then we never turn them on. So we don't start anything later, at any time later. Type 2 is being switched on and off most of the time, I would say. And type 2 is being turned on only once. So we have that in the third time period. This demonstrates us that the TSP problem that we have solved on the lecture was an integer programming problem. This time we have solved a mixed integer programming problem because one of our output was in fact a real variable, right? Its type was continuous. The output variable. Okay, looks good. There are several other examples. I would like to make sure that I actually cover the protein folding one, because this is an example that you cannot in fact run on your Colab notebook. You need to install a license on your local machine. So most probably, so if you have Python installed and you know how to use it with Bash, there should be no problem with that for you. You can just simply request an academic license, and you should be able to use. So this process is quite straightforward, and they have all of the necessary instructions being listed here on this website. And you should let me know if you have any problems with obtaining an academic license if you need one. Even though we cannot solve it with Colab notebook for the specific size at least, we cannot solve it just because it's too big. However, if we were to change the size of the problem, like put in less variables, we would definitely be able to solve it, even with the Colab. So let's take a look at what the problem is and what the model would be for protein solving. So protein solving is protein folding, obviously. So the problem is like the follows. You have a one-dimensional structure of a protein that consists of hydrophobic acids and hydrophilic acids. And hydrophobic acids are the things that are interesting to us in this case. So it is known that a protein can be, like, when it's being when it's actually like located in the universe, it's never really found in the form of a straight line, right? It has some two-dimensional structure and some three-dimensional structure, and predicting essentially its properties, its chemical properties and physical properties are being determined by its structure. So like very similar proteins can be designed. However, predicting the structure of the protein, it will take like the form of the protein that it will take when you are assembling it. We are assembling protein as a line essentially, and after you have assembled it's being folded by itself into a specific structure, and the structure is what defines its properties. And in order to design proteins that have specific properties, you would need to be able to predict structure into which it's folding by looking at the one-dimensional structure. And from the linear structure, you would need to predict the three-dimensional structure. In this specific problem, we are tasked not with three-dimensional protein folding, but with a two-dimensional protein folding. We are the three-dimensional protein folding is claimed to be solved by the AlphaFold AI developed by DeepMind. Here we are not aiming at that level of technological advancement. We just want to solve a two-dimensional problem. So in like what impacts folding of a protein, what defines it? It's the number of hydrophobic acids that are close together. So the protein achieves its minimum of potential energy when it has as many of hydrophobic acids close to one another as possible. So you can see it on the picture down here that having a protein of this linear structure, where the black dots represent the hydrophobic acids and the white, like the gray dots, represent the hydrophilic acids. We would need to construct some like zigzag that puts black dots close to one another as often as possible, as much as possible. So for And we are predicting that the state of the minimal energy, the state in which as many hydrophobic acids as possible are put close to one another, is the state in which we will eventually find our protein. And so we should, if we would like, so this essentially predicts the properties of a protein that we have assembled as a single line, which is a very important thing to be able to do in applications of healthcare or drug design. Okay, so I hope that there's enough motivation for us to solve this problem now. Let's take a look at how exactly it's given to us computationally in the code. So we have amino acids, which are the hydrophobic acids. We have their location. Essentially the numbers in the linear structure. We have that on the second position there's a hydrophobic acid, on the fourth position, the fifth position, and so forth. And in total, we have 50 acids in our chain. What we need to do is we need to predict the places in which folds are occurring. So our main decision variable here is going to be fold. Fold k is going to be equal to 1 if and only if a fold occurs between the kth and the k plus first acid in the chain. So basically, if this is this is the first, the second, third, fourth, fifth, sixth, seventh. So if our fold has happened between the 7th and the 8th acids, then our fold 7 should be equal to 1. Otherwise, it should be equal to 0. Another important decision variable that will in fact play the key role in our objective function is the match. So we say that match ij is going to be equal to 1 if and only if a hydrophobic acid I is being matched with acid J for all hydrophobic acids I less than J. In this example, we have our fourth hydrophobic acid being matched with 5, 6, 7, 8, 9, 10, 11. So our fourth is being matched with 11th. Therefore, our x for 11 should be equal to 1. Otherwise, it should be equal to 0. This match is being defined only for hydrophobic acid, as we don't care about the hydrophilic ones. So they can be matched, they can be not matched, it doesn't matter. Okay, so now we need to put this notion of folding into mathematical form. So we need to put down the constraints. First of all, we need to understand how exactly folding is happening. So folding is happening. Matching. So we are matching between a number I and a number j if and only if our folding has happened exactly in between them. So in other words, xij can be a match at if essentially only if there is a folding has happened at location k, where k is I plus j minus 1 over 2. So we need to but essentially if we have a match between 4 and 11, somewhere between exactly in the middle between 4 and 11, a fold has had to happen. And in how to express what in between means, or exactly between means, this is what it essentially means. So we know that 4 plus 11 is 15, and 15 minus 1 is 14, and 14 over 2 is 7, which is exactly the location of this fold. So we just need to carefully calculate the middle in the space of indices. Okay, and this constraint prevents us from having extra matches that are not determined by any folding. What else might happen is that it could be the case that there is a fold between two like let's say that this asset was to be a hydrophobic asset, right? Then between this asset and this asset, there is a fold exactly in between them, this one. However, there is a fold that happened, there's another fold that happened between them. Therefore, we need to prevent matchings for cases when we have several folds between two assets. How to put this down in form of a constraint? You need to make sure that the summation of yk and xij is less than or equal than 1 for any k between I and j, except for probably the middle one. So basically, this is saying that if you have xj being equal to 1, then yk must be equal to 0 for any asset in between I and j, except for probably the middle one. And in fact, the middle one has to be a fold just due to this constraint. Okay, so these two constraints take care of capturing the protein structure, the two-dimensional protein structure. Okay, and our yeah, so essentially our objective function is the number of the total number of matchings. So this is essentially the sum over the entire fold of xij of the matchings. Okay, so how do we put this into the form of a program? Well, we need to do some magic with indices first. So here it's called pre-processing, but it's really just creating index sets. This is the most important part of this problem. So first you need to create the list of IJs, the list of all of the pairs IJ for which matching is in fact important. So this is gonna be a list of pairs of I and j such that on the ith and on the jth location there is a hydrophobic asset. How to fill it up? So basically, first you make sure that you do not account for those hydrophobic acids that go one after the other. So for example, regarding these two acids, we don't care if they're close or not, because they are close just by definition. We only care if they are close if they are not neighbors. So we're not going to be putting neighbors into this list, into the list of IJs. and this condition prevents us from putting in neighbors. So we want j to be greater than I plus 1. So I is the smaller number, going to be the smaller location, and the j is going to be the larger location. And if in fact they're not neighbors, then we put them into the list. We use a special tuple list type of GurobiPy. Now we create two additional lists in which we're gonna be putting all of the indices that are between I and j that that either are in between, so okay. List ik1j is going to be the list of the locations in the middle between the two points I and j, and the list ik2j is going to be the list of all of the it's the other way around. Okay, so let's just take a look. So if we are going over all of the locations k between I and j, we are putting a location like a tuple ijk into the list 2 if our k is in fact in the middle between I and j. If k is not in the middle between I and j, we put it into the first list. So this gets us this separates this case from this case, the first case from the second case. The first list is going to correspond to the second constraint, and the second list is going to correspond to the first constraint. I have no idea why they decided to do it this way, but anyway. Again, we're going to be using the GurobiPy tuple lists. Matching that are enabled by folding are going to be called list ijfold, and we are putting down all of the possible ij's for which k is okay, like for which k would be in the middle of ij. So these are the matches that are possible to make by folding, essentially, because there are matchings that are impossible. So we put down all of the list of pairs I and j for which folding, like matching by folding is possible. This is also going to be the GurobiPy tuple list. After that, we would need to define the model, and so this pre-processing takes care of the most of the hard work in this problem, and it's going to be quite a common thing in the problems, and we will there is a homework question that requires you to think more about pre-processing and putting down indices correctly more than anything else. So first of all, you would need to define a model. You would need to define variables, the matching and the folding variable. So this is the match variable is corresponds to x in the model, and the fold variable corresponds to y in the model. You can put down the two constraints. The first constraint is being put down for the list the first list, and the second constraint is being put down for the second list. Apparently, they are indeed determined for the two constraints. Oh, okay, yeah, that's right. Okay, so the second list is in fact being created for the second constraint. It's all right. So we put down the constraints using the two lists that we have previously crafted for them. And we put down the objective function using the ijfold list that we have crafted as well. The list of pairs between which we can arrange a matching by using fold. After that, we'll only the only thing that we need to do is to ask the GurobiPy to solve the problem, and then output the optimal matchings in sequence. So eventually, we found out that this particular structure is the optimal structure for the specific protein that we have designed. After that, we would just toss it over to scientists that can use this information. Okay, so these were the two examples that I wanted to demonstrate today. Let me know if you have any questions. See you all on Thursday.